dominated by Anglo-Saxons, I might add. Is Professor Yates, who obtained his BA degree from the University of Cambridge and an MSc MA in radioastronomy and theoretical physics before completing his PhD at the University of Manchester. I was unsuccessful using the internet to dig into all of Professor Yates' postgraduate details. Disappointing about the internet in that sense. He's currently a professor in the Department of Physics and Astronomy at the University College London, a member of the Center for Computational Science at UCL, and chair of the National Infrastructure Project Directors Group. Research interests include star formation and photon-driven astrochemistry, mass loss from evolved stars, evolution of starburst regions, properties of astrophysical dust, radio transport of dust, and gas, that's close to my heart, and of course computational astrophysics, and today he's going to talk about the role of computing in scientific inquiry.
Good morning, everyone. I'm very aware that I might be keeping you from your lunch, so I will try and move quite smartly. Apologies for being an Anglo-Saxon. What can I say? So what I've done here is I've listed all the things I'm currently involved with, and this isn't an act of self-aggrandizement. It's actually trying to give everyone a sense that computing is now very, very much part of certainly the UK's look forward about what we need to invest in and what we need to be good at going forward. So I'm the director of DIRAC, which is the entity that provides high performance computing and data intensive research computing facilities for particle physics, astrophysics and nuclear physics. So we support the simulation and data analytic community in the UK. As of today, I'm now the co-chair of the UK National Infrastructure Project Directors Group. I was it for 4 years. Yesterday, thank heavens, was my last day. So, but they've kept me on, and this is the main group across the Research Council that's kind of reorganising and bringing together all the various computational activities across the academic disciplines. For my sins, I sit on the Research Council UK Infrastructure Group, which didn't exist 3 years ago. It's quite new, and it's actually done an awful lot of work. And one thing that we called into being 2 years ago was the Research UK Cloud Working Group. And I'm the secretary, but only in name only, really. I think my main job is to make sure they do things. So you probably gathered I'm a baryon physicist, really. It's nice to hear them described as messy and complicated. A colleague of mine last week described them as confusing. So it's nice to know that we're confusing. So computing, it's actually got a very long history. And remember that computers were once people. So if you look at the Royal Greenwich Observatory in the 19th century, people who worked out things from equations, they were mostly women, they were called computers. They were actually working out orbits and things like that. If you look at computational fluid dynamics in the 50s and 60s, when people were actually working out hydrodynamics, the computer was a very large warehouse with lots of desks in rows, and at each desk there will be sat a woman, and they would be working out the cofactors and determinants of all the little matrices, and they would bring their work up to the next set of tables and so on until there was a solution to the matrix. And so the wing properties had been worked out. So for a long time, the kind of way we solved things was through procedure, through careful procedure and using precision. And it was very often people. We've had mechanical machines to help us for a long time, so the abacus, you can think of that. And if you look at, say, what Lemaître was, if you look in the early 19th century, the idea of using mechanical machines to work things out, so the difference engine that Babbage used and Lovelace helped him with the programming of that. He didn't quite finish the difference engine, which would have been the first differential analyzer, but he certainly had it written down. And then if you look in the early 20th century, we were starting to build mechanical devices that were doing differential calculus, and Carl showed the Stormer effect work that Lemaître did, and he was using, state-of-the-art differential analyzers in order to solve those very nasty sets of equations. And then from about the 1950s, we've had our hands on electronic computers, which revolutionised things because it's allowed miniaturisation and increased speeds. So you could do more calculations. So I've got scientific inquiry. The last talk I went to at the Research Council's UK last month, when we were thinking about all of this, was we were told that there are now 4 pillars of scientific inquiry. So there's observations and experiment theory, where we produce abstract mathematical expressions to sort of guide us through reality. And then there were 2 new ones that I'd kind of missed, actually. So simulation is the 3rd pillar, and apparently it's been and gone, which dates from the 60s, and we're now in a new age. So there is now the 4th pillar, which is data-intensive research, which is the newest pillar. I think 3 and 4 have got far more to do with getting money out of the government than they do about how we. It's a sort of a new radical paradigm, because if you look back through history, people have been doing simulation. So Lemaître was doing that in the 30s and 40s. And if you look at data-intensive research, well, every time we produced a major survey in the past, even though it was on paper, new things were discovered from it. So data for discovery has been around for an awful long time. Len and I like the example of Kepler deducing laws of gravitation, of planetary motion from Tycho Brahe's great survey. And that's been going on all the time. So there's nothing new under the sun, so I've got my biblical quote in there. However, if you look at what the people on Dirac do, we still propose testable hypotheses, and we even test them. We actually confront simulation theory with the data, and we also still survey, and we look at the the data for empirical meaning and correlation. So all this is still going on. It might be going on at a far greater scale, but we're still doing stuff that's recognisable to what we were doing 200, 300 years ago. So I thought I'd do a quick survey on what Dirac's doing on cosmology at the moment, so sort of going back in time. So if we go to the primeval atom bit, we have a very active programme led by Swansea in the UK, where they are modelling the quark gluon plasma, seeing how the very early universe was changing with the interactions of these fundamental particles. We've actually got a very big programme where people are trying to add gravity to the standard model of particle physics, and they keep crashing our petaflop computing system when they try this. So there is still a bit more to do on that. It is very hard, as we pointed out. We've done an awful lot of work, and Paul Scheller will know far more about this than me, testing the concordance model of cosmology. I think that's actually been one of the triumphs of Dirac too. We made a great contribution to that. Also, in terms of gravitation, people you've been saying, why look for dark matter particles? Well, people spent an awful long time looking for gravitational waves, and we found them last year, after 30, 40 years. One of the nice things for Dirac is that we did all the post detection modelling. So we were the ones that Mark Hannam at Cardiff and his group used our systems to actually produce the bits and deduce it was to black holes coming and merging. We've now got very big programs looking at what are dark matter and dark energy. So dark energy survey was mentioned earlier on. We have a very big analysis program looking at gravitational lensing, so we can measure over those 40 days and 40 nights what the actual matter distribution on the sky actually is. We do an awful lot on how did the first structures in the universe grow and evolve to the structures that we see today. So we've been doing simulations that have taken about 8 months. So that's Carlos Frank's group up at Durham. And actually, one of the nice things that we're kind of seeing in recent proposals, so we're seeing more string theories coming in, we're seeing people asking the question as to what physically is a Big Bang, and what was yesterday if there was a yesterday. So we're starting to see all of these things beginning to appear now. And you're probably gathering it's a lot of fun being the director, because you actually see all these threads coming together. So we're still waiting for our third tranche of money, which we hope to get in the next couple of weeks, and so that will provide a huge boost to this kind of research. Okay. So one of the things that we've been banging on about within the Dirac project, because we do represent essentially half of theoretical physics in the UK, is this whole notion of quantifiable uncertainty. It is, I think, one of our greatest strengths as scientists or as natural philosophers, is that we're prepared to try and measure just how, not how wrong we are, but how uncertain our results are. And within one of our research councils, there is a whole grant line now to actually determine better ways of quantifying uncertainty. We are measurers. We do measure stuff. Some of our huge data sets that we've produced from simulations now are indeed data sets in themselves. We're starting to get to the stage where some of our simulations are actually used as data sources. So it's important to know what the uncertainties are. We know our theories are incomplete. Humidity is important. So they also contain uncertainties. And the nice thing about computation now, it allows us to quickly and easily determine the uncertainness of our understanding. So as we compare data with its uncertainty with our models and simulations with their uncertainties, we are able to get a quantifiable understanding of what the uncertainties are. And it's good because it tells us how we're doing, it does give us new insight, and it obviously tells us what to do next. I think that this is something that I've seen grow over the last 4 years. A lot of the things that the cosmologists have been doing, especially around Bayesian analysis, are now spreading out into the other astrophysics disciplines, and we're starting to see them leaping over and into other academic disciplines as well. So the cosmologists have actually really driven this, and it's been very good to see. It's not all doom and gloom. We do have some very exact theories. I am a spectroscopist by heart. So we have lattice quantum chromodynamics, that's doing an excellent job now in producing data that you can trust. And quantum spectroscopy, of course, has been one of the great triumphs over the last 40 years. And being from UCL, where I'm very proud of this because it was Mike Seaton's group in the 60s that really drove this. So both these communities have developed computer programs that just tell us how the universe is. And that's really good. That's one of the things that we all want to get to, and there are examples of that now. So we can use the outputs of these computer predictions safe in the knowledge that they are some of the truest things that we know. We can actually trust them without having to go off and measure them. That's the really important thing. So there are bits of physics where we're now able to do that. And these are actually very complex, very nasty problems. They're actually some of the nastiest problems that are solved on Dirac systems. So, where are we now? Computing is changing very quickly. That's why I sit on so many committees and groups, because we're suddenly in an era where there is profound change. Part of this is driven by the sheer scale of the data that are being generated. And what we're finding is that our old designs and the technological assumptions that we were making, and our software and our compilers really aren't quite ready for that. So a lot of us are having to very quickly become computer scientists as well as our day job in order to cope. So it's changing us. And it's also changing scientific culture, not in a good way, because because it's become ubiquitous, it's been treated as a utility, and time again we're seeing people trust what's coming out of a computer in a way that they wouldn't trust what's coming out of an experiment. And this is an education problem that we really do need to get on top of. So that they are scientific instruments. And certainly we've now come to recognise, and hopefully recognise with lots of money soon, that computing is recognised as a foundation stone of modern natural philosophy or science. All the things that have been talked about this morning would not have been possible without computers. And sort of one thing I would say, it's a bit easier in Lemaître's day. It was much more obvious that they were scientific instruments. You know. I think that's one of the things that we have to remember. So what are the changes that are coming? So there's a buzzword. I'm afraid you have to blame me for this one. I think I was the first to use it about 4 years ago, certainly in the UK context. Democratisation. There'll be a huge increase in the user base, even within our own quite narrow subject areas. We've seen medicine, biology and social science, and I'll include economics in that. They're now on an equal footing with the physical sciences and engineering. Their problems are huge, and I think it's nice to realise, and it's nice seeing the social scientists and economics realising that their problems are incredibly complex. I think they did take a beating in 2008 and 2009 for getting things so wrong. So there is now much more of a move to get social science, biology and medicine really engaged, and also we physical scientists are discovering that in some areas they're way ahead of us. So Johannes mentioned machine learning, but also in the way we look at data and other things like that. We're seeing much more use in the formulation of theory and in experimental design. Data for discovery is going to be a very big theme, and people keep going on about deducing physical laws from the huge amounts of data that we will have. And for me, one of the big things that goes back to the instrumentation idea again is that our problems have now got so complicated and so challenging that the IT manufacturers are now interested in working with us again in a big way. So we're starting to see much more co-design of systems. to actually solve our problems. We went through an era of commodity phase, just buying things off the shelf and coping with it. We're now becoming instrumentalists again, which is really exciting. And we're also having to really look at how we program and code up, because many of the things that are now appearing are very different from the things that we were used to using through the long era of the Xeon processor. We had 15 years of relative calm. That's all over now. So, in a big sense, we're very much going back to the 70s and the early 80s. So things are changing. So that's all I have to say. I hope that, yes, I just finished in time for lunch. So thank you very much for listening.
Thank you so much, Jeremy. Any questions for Jeremy?
Well, when electronic computing started in the, say, late 1960s, we had a very strong restriction on storage. Now, these days, it seems storage there is no limit, but data are coming in at an enormous rate. Is there no limit to storage? Is that problem solved, or where are we there?
The key bottleneck now is the interconnect, which is the networking. Okay, because it's the kind of growth in the capability of that technology is much slower than the storage and CPUs and other systems. So one of the things that quite a few of us have done over the last 4 years is make use of, is actually take the very fast storage elements that used to be, networking elements, that used to be close to the chip, and actually take them outside and use those technologies so that we can do things between nodes and storage elements. So we are trying to solve the network bottleneck, which is the real problem.
Another question?
Thank you for the talk. Sorry, could you say again, in what way does the physical sciences community stand to learn from the bioscience? What is it they're better at? About
Metadata,
meaning the
meaning
management of databases.
the management of databases, the application of metadata that's readable by the entire community.
Because their words are more comprehensible than the words in physics to a person who's not an expert.
No, they would disagree with you on that.
Read
Vehemently.
Science magazine regularly.
They would vehemently disagree with you on that. So, I mean, I chaired the data infrastructure working group for the last 2 years, and I have been left quite ashamed by my own community, actually, just how well they do it. Okay, and their communitarian way of looking at things. So you know, we have a lot to learn from them. I think the other thing that we're picking up is that they were very early adopters of using machine learning to pick out patterns. Okay, it's a simple problem, GCAT and all that, but they did it. Okay, and you actually see within there, it's quite odd, because you actually see this very clever machine learning layer, and then you look at the rest of the codes, and it's absolutely awful. So they're very bad programmers, but they're very good at using machine learning. So they can learn a lot from us about how to program properly and things like that. But they were very early adopters of machine learning and using very advanced statistical methods as well. Not as advanced as the cosmologists are, but still very advanced.
Chemists had to learn very early because of gene shift technology.
Yeah.
There's no way they had to use very sophisticated systems.
Yeah.
One more question over here.
Yeah, maybe it's related, but deducing physical laws from huge databases, do computers, are computers able to find laws that we may not be able to find ourselves?
There are lots of people who say so.
Has it been?
No.
Yeah, but for instance, Kepler can, we do history now, and if the data in the computer can recover what Kepler did.
I'd love to see one. I'd love to see someone try that. But when we go to these big data meetings, it's one thing that's said time and time and time again, and yet you never see an example of it.
And Lee, was that question for us?
Can you give us some examples of the leverage of the method in these context?
I think for me, it's. I recognise that we're back in that time. Back in that time between the 30s, 40s, and 50s, that things are, we're having to get involved with the fundamentals of computing technology again. And I mean right down to the level of feeding data from the disk along the interconnect onto the cache itself, and which is what the processor actually works on, and that is causing us to having to reevaluate how we program. It's making us it's making us get much more involved in the design of the optics. That is what we're and in the design of the disk systems, and actually in the design of the cache and chip systems. And I've just broken a large number of NDAs by telling you that. Okay, so it's really at that level now, because people like Joe and others are going to be producing so much data. If we don't deal with this, it's going to take a long time. So that these big projects like the LSST, like square kilometre array that's coming along, they're driving all this innovation. And reading the accounts of what Lemaître was doing, we're doing the same thing. And we kind of haven't done that for a while. So it is very exciting getting back into that mindset again of looking at computers as instruments. And I'm hoping that by doing that, we'll stop the bad cultural change where people just believe what a computer says. That's got to end. And you're all PhD supervisors. Make sure it ends. Okay, thank you.
Okay, thank you so much.